Hi everyone, I'd like to welcome you to the talk titled Growing the Quantum Open Source Ecosystem. So I'd like to introduce Nate Stemen, who is a member of the technical staff at the Unitary Fund. So I will go ahead and turn the time over to him.
Great, thank you so much for the introduction, and thank you everyone for being here, and thank you to the conference organizers for putting on such a nice event. So today, we'll be talking about the quantum open source ecosystem, and I'm going to tell you quite a few different things today, but just to give an outline. So I'm going to try to give a very brief and non-technical introduction to quantum computing. We're just going to do a very brief flyover. This is not a technical talk. You will not walk away understanding quantum computation unless you already do, and more so just so we can orient ourselves, we can understand what quantum computation is and why we focus on growing an open source ecosystem surrounding it. And then I'll tell you a little bit about where I work, Unitary Fund, and the ecosystem that we are trying to develop, or that we are developing. And so let's jump straight into it. All right, so what is quantum computation? That's really the question we need to start with. And to answer this question, like I said, it's not going to be technical. It's going to be kind of a more historical and just quick flyover about what quantum computation is. So one way to think about quantum computation is to think about how science and history and particular technological revolutions have kind of interplayed. And so when thermodynamics first kind of started being studied in the 15, 16, 1700s, we started using that understanding of how heat, energy, entropy, how all of these concepts relate, and we were able to use those to build new machinery that took advantage of that newfound scientific understanding. And there was a lot of interplay. We would build machines, and then we would later scientifically understand them, and there's a huge interplay there. And this is playing pretty fast and loose with some of the history, but this is, this tracks with other things as well. So for example, electrodynamics. We were able to understand, how do electric fields, how do magnetic fields, how do they interact? And we were able to use that understanding of this field of science and physics to then build technologies that harnessed that understanding. And again, there was a lot of interplay, and you can see here, we have some of the early computers, and down here on the bottom right, a computer that is requiring multiple people to kind of get it running, and it requires like expert operators, and not necessarily easy to use technology. And so, those are just two examples, and so quantum computation can kind of be framed in this light as well. And so we've had an understanding of the physics of quantum mechanics for roughly 100 years now. And just in case anyone is unfamiliar, quantum mechanics is the field of physics where we study the very, very small things like atoms and molecules. And so we've understand how to model these systems, like I said, for 100 years. And we have some quantum technologies that have come of this. For example, lasers are a fundamentally quantum technology, and we use those in our everyday life. But kind of the pinnacle of what we have dreamt of for using quantum is a quantum computer. So using these new laws of physics that we've discovered, maybe not so new anymore, but using them to do computation in some way. Like, is there a way that we can use quantum mechanics to compute like we do on a classical computer? And so this is, on the top right here, this is a picture of one of the existing quantum computers that I think this is either an IBM or Google machine. As you can see, it's a very chandelier-like structure, and this is an example of a superconducting quantum computer. And they're very, very complicated machines. Here on the bottom right, we have an example of a quantum computer that's using photons to do the computation. And so that's kind of like what a way to think about quantum computers is this historical back and forth between science and technology, and we've had an understanding of quantum mechanics. Now we're trying to really get it to do something for us, and so quantum computation is potentially the thing that we can use our understanding of quantum mechanics to do. And so the question is, like, where are we now? And so I showed the picture earlier of these two women working at this like very early humongous computer, and I've put the picture of the Google device on top of that because that's kind of the point that we're at. We have working devices, but they're very, very limited in their capacity. They're very, very difficult to operate. This entire thing that you see here needs to go into a refrigerator, which is cooled to almost 0 Kelvin, basically the coldest things that we've created on Earth, and they're not very good. Is basically the answer at the moment. And so there's two kinds of axes that we need to look at. Is one, how much, what is the number of qubits that we can do computation with? And I'll introduce briefly what a qubit is in one of the next slides. But it's basically the thing that we're doing computation on, like the information that we're computing on. So how many qubits do we have? And then also, when we try to tell a qubit to do something, how frequently does it actually do that thing, and how frequently does it do something else? So what is the error rate when we try to do these computations? And right now, we don't have a lot of qubits, and we're not good at controlling the qubits. So we're not able to do the computations that we really would like these machines to do. So there's kind of two axes that we need to push on. One, like scaling our hardware to have more qubits, and then two, pushing down the error rate and having better control of these qubits. And that's kind of where we're going, because there are some potential applications of quantum computing that require us to have kind of much better control and many more qubits than we currently have. Right, so what is quantum expected to do? So there's this really nice quote from Richard Feynman, who was one of the first people to dream up quantum computation as a concept, and not necessarily the first, but he said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." And in particular, one of the things that Feynman was interested in and was using quantum to simulate quantum, because the laws of nature for quantum mechanics can be very complicated partial differential equations that are very complicated to solve numerically, or they just scale very poorly as you increase your system size. And so if you can use quantum itself to simulate, for example, chemistry problems, we potentially have much faster, we can get answers much faster. And so that's one of the first kind of applications of quantum, is to do chemistry simulations. So there's two kind of interesting things, I think, here. The first being drug discovery. A lot of people want to use quantum computers once they are kind of at scale to simulate how a potential drug could interact with the human body. So it's a lot of work that has to undergo between finding a chemical and then doing human testing. And part of that is trying to understand, like, when a human ingests this chemical, what is going to happen. And there's just so many possibilities, and so using a quantum computer to simulate exactly how molecules are going to interact with each individual part of whatever part of the body you're interested in could be potentially very useful. The other potential application is forecasting. I can't say I know a whole lot about this, but I know that there's a lot of banks that are interested in quantum computation for its potential to be able to forecast whatever it is they're trading in a more efficient manner, or do better pricing. And then finally, potentially the thing that people have heard most about is quantum computers have the potential to break things like RSA encryption, which is or the encryption that we use to secure internet communications. And this is true. It does. This is actually one of the first algorithms that kind of put quantum computing on the map in the 90s, was by a man named Peter Shor. and his algorithm was basically a much more efficient algorithm for factoring integers, and that's kind of one of the problems that underlies our current internet security. And so it's not something that we really have to worry about now, because like I said, our existing quantum computers are very, very small, and they're not even close to capable of factoring the size of integers that would be necessary to break or to spy on someone's internet traffic and decrypt what they're seeing. But governments are interested, and this is kind of what put quantum computing on the map for a lot of governments, and said, oh, okay, maybe we should be paying attention to this field. And also don't worry, because there's lots of post-quantum cryptography that is resilient to quantum computers, or at least we think so. So we are transitioning already in some areas. All right, so now the question is, okay, great, Nate, like I see there's potential usefulness of this in our society, but like why here at PyData? Like, why is this interesting to people that might be here? And so first of all, the things that you kind of need to know to do quantum computing have quite a big overlap with what people I think here might know, at least on the mathematical side. So the things you need to know: some calculus. That's kind of underlying a lot of machine learning and data science. We know that kind of stuff. A linear algebra. A lot of machine learning is linear algebra. We know that. And then quantum is also a lot of more linear algebra. There's a ton of linear algebra. And then there's some other things that go into the quantum. But my point is that there's a lot of overlap in the mathematical kind of ideas that underlie these fields. And if you're interested, this is kind of like the Bible that people learn basics of quantum computation by, and it's getting old, but it still does a great job. So that's just a resource for you. The second thing that I think is potentially interesting about quantum to people here is when you do a computation that is resource intensive, you sometimes outsource part of that computation to a particular part of your computer. And so this is a picture of a CPU, and sometimes you might want to outsource part of your computation to a GPU. And there's also other things. For example, this is a picture of a tensor processing unit, which can speed up parts of certain certain computations. And this is a picture of a QPU, which is a quantum processing unit. And so there is hope that in the future you may be able to take your complicated, maybe you're training a machine learning model, and there's part of it that you can send to a quantum computer to train more efficiently than it would be to do on your laptop or whatever supercomputer you're using. So yeah, it's good to have some familiarity with some of the things that you might potentially be using in the future, if maybe it's not a few years away, but still. And then, yeah, like I highlighted here, the programming aspect of things is quite similar. So I think I do want to show you what a quantum program looks like, but I need to introduce some terminology first. So like I said before, we have qubits. That's the fundamental piece of information, I guess, that we operate on. So instead of a classical bit that can be a 0 or a 1, we have a qubit, which can kind of be any point on this sphere. So maybe that gives you some intuition about why quantum computers are potentially more powerful or more efficient at doing certain things, is because you have like a larger space to do computation with. And then on the right here, this is a picture of what a quantum program looks like, at least in the original kind of formulations of what dreamt up by mathematicians and physicists. And so in the picture, starting on the left, you have 3 qubits. That's what we would have. And then each one of these boxes is kind of like an operation. And you don't need to know what the operations do, but this is called a circuit. And this is how a lot of quantum algorithms are specified. And it's maybe strange, but that's how kind of the physics happened, and then it is transitioning into a technology, and so it's, the pictures are nice though, and they do a good job of representing some of the things that we want to do. So those are the two terminology. We have qubits and we have circuits. And you can see how it might be similar to like an electrical circuit diagram or something like that. And so now I want to show you, just so we can orient ourselves, what does a quantum program actually look like? And so there's two kind of possible, not just two, these are two of the most popular front ends, is what we would call it, to write a quantum program. The first one is called Circ. Let me zoom out a little bit. And it's the language that has been developed, or it's really a domain-specific language is what I think we should think about it as. But it's ultimately just a Python library. And so this is what a quantum program looks like. As you can see here, we kind of define our qubit that we're going to operate on. We define a circuit, and we put some operations in the circuit. And so I've put one here, which is we're going to do a NOT gate, but we're going to take the square root of the NOT gate. And that's not something that you can do on a classical computer because there's no operation on a classical computer. That's the square root of a NOT. And so we're just going to print out the circuit, and then we're going to simulate if we actually had a real qubit and we sent it through a square root of a NOT gate and then we measured it, what's going to happen? And so we can just run this, and just so we can see what it looks like. So here's our square root of a NOT, and then ultimately we ran with 20 repetitions. So we measured the 0 state 11 times, and we measured the 1 state 9 times. And there's some randomness involved. So every time I do this, we're going to get slightly different results, but that's the idea. And then I just want to show you what a relatively similar program, but with a different circuit, might look like in Qiskit, as another popular front end that people are using to write quantum programs. And this is the package developed by IBM. So here we're going to instantiate our quantum circuit. We're going to put some operations on the quantum circuit, and we're going to measure. And then again, we're going to simulate what happens. So we can do that. You can see we now have a circuit with 2 qubits, and when we run this, we only get the 0-0 state and the 1-1 state. So you could imagine, you could have a circuit that creates other possibilities as well. For example, a 0-1 state and a 1-0, something like that. So again, there is some randomness. So every time we run this, we will get different results. But that's just the general idea. And I just wanted to show this so that we can orient ourselves. A lot of people, I think, come to me and say, like, oh, quantum mechanics is so confusing, like, how could I ever go about, learning anything about quantum programming or quantum software? And it's really, like, it's just software. We're not doing anything different from machine learning. It's just a new language that you kind of need to understand. And yes, there's some complexity there, but it's not some alien thing that is impossible to learn. So I just want to hopefully dispel that a little bit. Okay, so now let's talk more about the software ecosystem. And so the two examples that I just showed are both in Python, and a lot of the ecosystem has been developed around Python. There are quite a few other options out there, but a lot of the popular languages and things that people are using are written in Python. So, and as you can see from this very quantitative graph, there's a lot of options today. So for whatever you want to do, we just showed the two options to write circuits, but there's lots of other things that you can do with these quantum programming languages or packages, and so the thing that I guess I want to highlight here is that a lot of the quantum stuff started out in research, and so there's some there was some, how to say, like, impetus to open source things, because when you're doing research, you're sometimes incentivized to do such, and then really once once quantum computation kind of like started coming on the scene of like becoming a real technology, or starting that transition kind of like in this 2016, 2017, I know things were happening before that too, but I think there was like an intentional openness in early industry to put things out there, and I think, you know, from the academic history and then kind of like this intentional openness in early industry, we have like a pretty solid bedrock of things that are available to us, and that has allowed us to start building this ecosystem that we hope to continue to build and make more robust. And this is kind of the way that we like to think about having an open source community, is like not only do we want to have a lot of trees, but we also recognize there's a lot of other components to having an open source ecosystem that makes it sustainable and that makes flourishing possible. So a lot of people, when they go into a forest, they want to go find the big redwood and they want to look at that, and that's very beautiful. But what made that redwood possible is like the rich soil underneath it, and so there's a lot of components that we need to nurture to grow an effective and diverse and flourishing ecosystem, and this is maybe why you see I had so many animals in some of the previous slides, is just trying to stream this together in some way. Okay, so now we want to talk more about the ecosystem. We need to talk a little bit about Unitary Fund and what we do. So Unitary Fund is a nonprofit organization whose mission is to grow the quantum open source ecosystem and make it accessible to the most people that we can. And so there are kind of two pillars to our work here. I guess before that, we can kind of think of Unitary Fund as like a NumFOCUS kind of organization, but with a particular focus on quantum technology. And so our two pillars are, we run a microgrant program, and then we perform our own in-house research and software writing, programming, really. So the microgrant program is kind of like the big form of outreach that we do. So I want to save that for the second part, and I'll just talk briefly about the research that we do. So like I showed you, there are big players in the industry developing open source software, which is amazing. But that means that, there may be sprouting up these big trees, but there's lots of things that need to happen between the trees to make the ecosystem useful. And we need some of these smaller shrubs down on the ground in order to make our jungle as beautiful as really we like it. And so we recognize that there are products or packages that are not necessarily incentivized by individual companies or for-profit organizations to make. And so that's kind of some of the things that we are trying to build. I won't go too much into the details, but one project that we have is Mythic. If you ever come across any quantum open source project, there's a 99% chance there's a Q forced into the name somewhere, and so we are no stranger to that effect. So Mythic is an open source error mitigating compiler, and that's mostly what I work on. And then we also have Metric, which is a community quantum benchmarking platform. So we're in the very early stages of quantum computers, and we need to understand, how does IBM's quantum computer compare to Google's, and how does that compare to PennyLane, Xanadu, and so this is kind of becoming the go-to platform to kind of compare and contrast what are the options out there. So that's one of the ways that we're kind of trying to fill in gaps in the ecosystem, is by spending our own time and resources on building some of those. And then the microgrant program. So the microgrant program is a $4,000 microgrant, and no strings attached. We're not trying to gain ownership over anything. We're really here to create this flourishing ecosystem that we can envision. And we provide mentorship. Most of our micro grants have been for open source software, but we have funded other things, for example, online events, educational resources, and generally things that benefit many people. We're not interested in funding necessarily like private events and things. We're really dedicated to making sure that everything that we fund can be accessible to anyone who's interested. And so thus far, I think we've given 72 micro grants. I think we've actually given a few more since this number was updated, but they haven't been announced. So a few more coming. And yeah, it's really a global phenomenon. We've given to 23 different countries, and it's led to quite a few different publications. So people, write their software and then use it in their research and make publications about it. And yeah, we've had over 30 different libraries. 2 startups have been spun out or have been we've funded, kind of helped start 2 startups, and also a nonprofit. And really the microgrant program is aimed at people who are interested in exploring. And so we recognize $4,000 is not enough to sustain an individual for a long period of time, but for people, for students who maybe have a grad student stipend already, this can really be a nice benefit to them to kind of take the code that they've written as part of their research and maybe bundle it in a way that is more digestible for other people and make it more useful to the broader community. Because a lot of times research software, as I'm sure many are aware, it gets used for research and then it kind of gets thrown in the trash, and maybe another grad student picks it up at some later point in time, but it's not usually written in a form that is accessible for anyone else to use. And so this is part of the idea with the microgrant, is just to make some of these really cool projects a little bit more sustainable. And yeah, again, going back to this analogy with the jungle, like Circ and Qiskit, the two packages that I've showed, they're creating these kind of silos, and don't get me wrong, like, they are amazing and we need them, and we're just trying to help encourage the growth kind of between those silos, and like I said, like the ground layer and the canopy layer and these kind of things. So that's kind of our mission with the microgrant. Another benefit to the microgrant program is workforce development. And this is actually a pretty big component to quantum, because as quantum has become more and more hyped, for better or for worse, a lot of companies are trying to hire people who are capable at doing quantum-related things. And right now, it's not a lot of people. There are far more jobs in quantum than there are people who are qualified to do those jobs. And so a lot of the grants that we've given are people who are like just breaking into the industry, and it gives them kind of their foot in the door, and they can say to a prospective employer, like, hey, Unitary Fund gave me, they thought my idea was good, and they've funded my project, and I spent a few months working on this project, and it didn't have to just be a thing that I did on the side. And so yeah, I think we've helped break quite a few people into the industry, which is something that I think is really important and yeah, fulfilling as well. I think that's personally a really nice thing that we've helped do that. And then in addition, the community building aspect. So this is kind of goes into a few of the next things I'll talk about, but yeah, we've given 72 grants. That's quite a large community of people now, because a lot of the grants are given to teams. And so yeah, it's kind of a network of people who are accessible to talk to, and on our Discord, which I'll talk about in just a minute. So it's a group of people that, when other people come to us and want to ask, like, how do I use this fermion simulator or something? I can say, oh, okay, well, we funded that project, or we know someone who is working on that project, and we can help kind of people break into the field in that way as well. And these microgrants are going to building really like state-of-the-art software as well. It's not just hobby projects that are kind of fun for a few people, but not many others. So just to highlight a few of them, Crack is an open source quantum simulator, and it's performing better than a lot of the things that are being built by some of the research teams at companies. So it's performing really, really great, and that's by Dan Strano. QNetSim is we have protocols for running quantum computation, and so QNetSim was actually to do protocols for quantum networking. And that was for Stefan Diadamo. And then Daniel Tan received a microgrant to build a compiler, and again, it's performing better than some of the other projects that are out there as well. And so I just want to highlight here that yeah, these are serious projects, and they're really contributing to state-of-the-art research and state-of-the-art software. One of the other things that we do at Unitary Fund is, if we're trying to build this ecosystem, one thing we want to do is to understand who the ecosystem is and how we can serve to benefit it. So last year we ran the open source quantum survey, which you can think very much like the Stack Overflow developer survey, but again, more specific to kind of quantum. And so this is not nearly all of the data we collected, but it does just give you a sense of kind of who the people are. So like 55% of the respondents were researchers, which is relatively expected given that this is still very much a science and not totally a technology yet. But then a lot of people who classify themselves as software developers. So it is a lot of people who have just a relatively typical run-of-the-mill software development, maybe a little bit of a science bend, who are really getting interested in this stuff. And there's a lot of help that anyone who's interested can do without quantum knowledge. There's a lot of infrastructure that we're still setting up, and a lot of problems that are amenable without detailed knowledge of quantum computation and quantum mechanics. On the bottom left, we have kind of the software role breakdown, and so what kind of role do you play in your project? So are you a user? We can see a lot of people are users, but there's also a lot of project owner / contributor / maintainer. So like a lot of people are owning and contributing to and maintaining the software, rather than just having a majority of people who are users and a few maintainers. So I think that's actually really good that we have a great mixture of that. And then here on the bottom right, just kind of where people are getting their information about when they're working on some quantum software. Where do they go when we're stuck? And I think for me, this is just a great reminder that your documentation is so important. And I guess that's not something that's too unexpected. But then also we have a quantum computing stack exchange, which is getting pretty popular. So if you haven't seen that, maybe check it out. It's pretty interesting. The other thing that we do is every year we have put on a virtual hackathon called Unitary Hack. And this is a virtual hackathon aimed at getting people contributing to new projects. And so how we do this is we have open source quantum projects that are participating, and we give them usually it's around $300, which again we know it's not a whole lot, and they're able to take that money and distribute it across a set of bounties that they can put up for the hackathon. And then it's the one coming up this year is 3 weeks, and people can during those 3 weeks, people can open up pull requests and claim the bounty if the issue is closed by their pull request. And so last year we had 30 participating projects, and we distributed over 66 bounties for amounting over $3,000, and we had over 400 people participate. So I think it's a great way to get people participating and get people learning about new quantum software, and hopefully providing a little bit of financial incentive to get people kind of doing that. And yeah, maybe it doesn't feel so bad doing it on your weekend if you are able to get a little bit paid for it. And then finally, we run a Discord, so we host a few community calls on it. So like I said, Mythic, which is the project I work on, every Friday we meet to discuss our development. There's a few other projects on here as well, which garner some interest, and people are welcome to come and just hang out at these, listen, contribute in whatever ways they want. And then we have Quantum Wednesdays as well, which is kind of our weekly research meetings, where we're usually discussing a new research paper or something quantum computation related. And we use this Discord to kind of organize all of our projects and sorry, and have community hangouts and generally just hang out with anyone who wants to come by. And so how does it all work? We have a group of supporting members who donate money to us. I think a lot of the key players in quantum right now recognize that they are seeing a benefit from the work that we do, and so they are interested in helping us grow this microgrant program and like I said, growing this rich soil upon which the entire industry can benefit from. So we have these groups of people who have donated to us, and then in addition to these supporters, we also do our own research, and so we apply for government grants, and yeah, that is a pretty big portion of where we get our money as well. And in the last talk, there was a question about is the government funding some of this stuff, and the answer is yes. We do get government grants for some of our research, and then we also we recently were awarded this grant for this program, Pathways to Enable Open Source Ecosystems, and this is a National Science Foundation grant, and it's kind of just exactly what you'd expect. We're kind of using this opportunity to grow a larger ecosystem, and the government is fully backing this. So the answer is yes. The government is doing some work. Not to say that they couldn't do more, but it is happening. And with that, thank you everyone for coming, and thank you for the nice event.
So we do have a couple minutes for maybe one or two questions if anybody had a question. Okay.
Thanks. Do you know anything about the sort of quantum database thing? As I'm going to say, is that like a polynomial speed up? Is it just a complete bust? So it's just completely pointless. It's a nice bit of math somebody did in the 90s, but it has absolutely no future, practical applications because it's just never ever going to give you any worthwhile speed up.
So I think we're talking about Grover's algorithm, which is an algorithm to do unstructured search, and it is provably faster than any of the classical algorithms, which is interesting. In terms of applicability, I do think that there are some limitations, but I still think I think it is useful. I don't think it's just a piece of math. I think it will play into the quantum ecosystem eventually if we can build large enough quantum computers, and if we can get quantum memory to be a real thing.
Excellent, thank you.
Okay. Everyone, you can start to transition to your next talk if you would like to. And Nate, I believe you are here for the rest of the day.
Yeah, if anyone has any questions about quantum or about the ecosystem that we're trying to grow, please don't be afraid to talk to me.
Thank you so much, everyone.
Thank you.